Okay. Shall we start then?
Yeah.
Okay. Good afternoon, everyone. It's a great pleasure to invite Dr. Rajesh Kumar for this IITM special lecture. He will be talking on the implementation of brown carbon aerosols in WRF-Chem to understand the relative impacts of light-absorbing aerosol deposition in high mountain Asia. Dr. Rajesh is currently working as project scientist 3 at the National Center for Atmospheric Research, Colorado, USA. He did his PhD jointly from AWS Nainital and University of Hamburg, Germany, following which he worked as a postdoctoral fellow under NCAR Advanced Study Program, which marked the beginning of his journey at NCAR. His research area focuses on air quality monitoring, aerosol and chemistry-climate interactions, projection of future air quality, impact of air quality for public health and food security. He has immense contributions in the development of chemical parameterizations in the WRF-Chem model, as well as CMAC GSI chemical data assimilation system. He is also among the lead developers of the air quality early warning system for Delhi, which is a joint collaborative work between IITM and NCAR. I would now like to welcome Dr. Rajesh for his talk. Over to you, sir.
Yeah, thanks a lot, Shreyasi, for this kind introduction. Today, I'm going to share with you an ongoing project which focuses actually on constraining the deposition of light-absorbing aerosols in the Himalayas. And a big part of today's presentation will be focusing on implementation of brown carbon aerosols. So I would like to acknowledge my co-authors from NCAR, PNNL, and University of Arizona. And I would also like to acknowledge the NASA for funding this project under the HIMAC2 program. So a brief outline of this talk, I'll start with the project motivation and objectives. Then I will show some slides on multilinear regression-based analysis of the relevance of aerosols in high mountain Asia, implementation of brown carbon aerosols in WRF-Chem, implementation of black carbon tracers in WRF-Chem for source attribution analysis, and I will end with the current status of the project and a brief summary. So why do we care about high mountain Asia? We know that more than 1 billion people live in regions downstream of high mountain Asia and depend on high mountain Asia for their water needs, agricultural needs, etc. But high mountain Asia has also been susceptible to climate change, as has been covered by many studies and also covered in newspapers. Like, for example, this is an example from Global Citizen with the news article saying billions rely on Himalayan glaciers for water, but they are disappearing. So it's really a climate crisis, which people are not talking much about. There was another article in CNN that said ice took roughly 2,000 years to form on Mount Everest, but it took ice to roughly 2,000 years to form, but it has melted in around 25 because of the climate change. So snow is an important component of high mountain Asia, and here it is just a brief overview of the processes controlling snow cover in high mountain Asia. We can categorize these processes into three different categories. So the first thing is the meteorology. We know that snow and rain means snow is a part of precipitation, which is driven by atmospheric teleconnections. We know that the western disturbances as well as the Indian summer monsoon, they are main sources of precipitation in the high mountain Asia. So those are really driven by the atmospheric teleconnections. And then elevation is an important factor because elevation kind of determines whether the precipitation is occurring in the form of rain or snow. So that is another parameter that is important for high mountain Asia. And then the third is the aerosols. Here means I just put absorbing aerosols, but the scattering aerosols also play as important role in the system as the absorbing aerosols. In addition to some direct relationship between the snow cover in high mountain Asia, there is also interaction between these different processes. Like, for example, aerosols. They affect the meteorology. There are interactions between meteorology and elevations. So in the first analysis that we did in this project, our objective is to capture both these linear and non-linear interactions into a multilinear regression model. So here we try to represent YSCF, where SCF is snow cover fraction, as a function of the linear relationship between these three type of predictors, as well as non-linear interactions between them. So we use the satellite-derived snow cover fraction, and we use the meteorological and aerosol predictors from the existing reanalysis. This is just to show the snow cover fraction distribution in high mountain Asia. The top panel here, this is from the MODIS satellite, and the bottom panel is from ERA5 reanalysis. Actually, these products are available at different resolution. The MODIS satellite snow cover fraction is available at 0.05 degrees, while ERA5 is, I think, 40 kilometers. But we regrid them to 0.75 degree because that is the resolution of the cancer reanalysis. So we kind of coarse this data to make this data set coarse so that we bring everything together on a single grid. One thing that is that become clear from this figure is that ERA5 reanalysis overestimates the MODIS snow cover fraction, although it captures the spatial distribution. Means both the MODIS and ERA5 reanalysis shows that around the edges of the high mountain Asia, the snow cover is higher, and in the inner parts, the snow cover is lower. So following this, we divide the high mountain Asia into two types of regions, where the red boundaries, they kind of encompass high snow cover fraction. So we define it in this way: if the snow cover fraction is between 4 to 20%, we call it a high snow cover fraction region. And if it is less than 4%, sorry for the mistake here, if it is less than 4%, then it is a low snow cover fraction region. So those are mostly in the inner parts of the high mountain Asia. So what we do for our linear regression, multilinear regression model. So this is again the mean snow cover fraction from what is as was shown in the previous slide. Here we are showing the different predictors. So basically here I'm just showing true meter temperature and total cloud cover. But in fact, we take many meteorological predictors, which includes skin temperature, sensible and latent heat fluxes, cloud cover, total low, mid, high level cloud, dynamic circulation, sea level pressure, geopotential heights, 10-meter winds, moisture, aerosol mixing ratios, aerosol optical depth, which are our aerosol predictors. We use the elevation variables also as one of our predictors. So all these data sets are regraded to 0.75 degree, which is again the resolution of CAMS. Sorry, this. All right, and we have used a multilinear regression model that we are showing here. So the main effects, these represent the linear correlation between the snow cover fraction and individual aerosol meteorological and elevation predictors. And we use 351 nonlinear interaction terms as a quadratic function. So all variables are standardized before using the model. And here, say, for example, aerosol-aerosol interactions mean the interaction between AAOD and surface aerosols. So here we are looking at the relative importance of meteorological interactions versus aerosol-met interactions. What is happening? Met interactions and aerosol-met interactions. So you can see that meteorological interactions are more important than the aerosol meteorological interaction. The aerosol meteorological interaction in the, sorry about this, I'm not sure what is happening in my presentation. So the role of the aerosol meteorological interaction in the high snow cover region is nearly constant throughout the year. In the low snow cover region, which are the inner parts of the high mountain Asia, yeah, I'm sorry, something is happening, and I don't know what. I'll try to keep it stable. So okay, give me a second. I think this is somehow the transitions is enabled. Let me see. Hopefully this will fix it. All right, so here we see that like especially during the July, August, September period, the importance of meteorological interactions goes down and the importance of the aerosol meteorological interaction goes up. So this may have to do with the active Indian summer monsoon season, during which the deep convection transports the aerosols to higher elevations. So this is what we learned from this purely statistical analysis. This is a study that is under review in GRL. But certainly this multilinear regression analysis has several weaknesses. So first thing is that everything is done on a very coarse resolution, 0.75 degree. And brown carbon aerosols are not considered into this, which represents an absorbing fraction of the organic carbon. ERA 5 reanalysis does not include aerosol meteorology snow interactions, and we know that most of the global model, they severely underestimate aerosols in India, as shown in this figure, where Pan et al. 2015 compared a lot of global models against black carbon observations that are shown as bars here, and all the models are shown as individual lines. So you can see that especially during the winter time, there is a large underestimation of aerosols by the global models. Now, what this is doing is this, because we are underestimating the aerosols in the source region, we are also underestimating the aerosol absorption over the Indo-Gangetic plain. So here, what we did is we did WRF-Chem simulations from 1995 to 2004. This was from a previous study, and we compare the single scattering albedo from WRF-Chem with the aeronet observations of AAOD, single scattering albedo in Kanpur. And you can see that there is a large overestimation of single scattering albedo by the WRF-Chem model. And the radiative effects of aerosols are strongly sensitive to errors in single scattering albedo. So for example, this is a study which showed that 5% overestimation of dust single scattering albedo can change the direct radiative forcing of dust aerosols by 80 to 90% in South Asia, and by 20 to 50% over the downwind Indo-Gangetic plain region. Because we are also underestimating aerosol deposition in snow as well as the aerosol absorption. So here we are comparing black carbon in snow. This is the cumulative probability distribution function simulated by GeoScam in circles, and observed values are shown in pluses. Although there is a good match of BC in snow, but when we compare the black carbon absorption optical depth with the observation, you can see that GeoScam has a large underestimation. So if the aerosol absorption is underestimated, then the amount of radiation absorbed by these black carbon aerosols in snow will also be underestimated, which will lead to an underestimation of the snow melt and our uncertainty and our understanding of how these aerosols are affecting the water availability in downstream regions. So because of, for these, we defined the 3 science questions in this project. So the first is, what are the relative contributions of BC, dust and brown carbon to atmospheric and snow mediated radiative forcing and albedo reduction in high mountain Asia? Second was, what are the relative contributions of emissions from different Asian countries and rest of the world to light absorbing particle deposition in high mountain Asia? And the third is, how has lap deposition or high mountain Asia affected snow melt, runoff characteristics, and water resources in downstream Asian regions over the past 2 decades? So this is the workflow of our project. it's a busy slide, and this workflow has been divided into 3 tasks. So basically the yellow, the cyan, and this kind of orange color represents the 3 components of task 1, where task 1.1 is mostly to collect all the data that we need to run our WRF-Chem model, as well as the data that we need to assimilate, like for example here MODIS AOD, MOPIT CO, and other data sets that we need for evaluating the model. That includes both the satellite observations as well as in situ observations. Now, the second task was to implement a new brown carbon evolution scheme within the WRF-Chem model, because we know that the biofuel and biomass burning emissions dominate in Asia, and brown carbon is thought to be an important component of biofuel and biomass burning emissions. So if we want to improve our understanding of how aerosols affect the glaciers in the high mountain Asia, it is important to include brown carbon aerosols. So that is included as a separate subtask. Task 1.3 is then to implement, to develop a data assimilation system to constrain the aerosol burden in the model. And I'll show you later in my presentation that why is it important to assimilate the satellite observations, how much benefit we can get by assimilating those observations. So once that is completed, we will thoroughly evaluate the model against these multi-platform observations. And then we have also developed a tag tracer technique within the model to look at the source attribution analysis for lab deposition in the Himalayas. So the idea behind this source attribution exercise is to understand what Asian countries are contributing the most to light absorbing particle deposition in high mountain Asia. We also plan to do an uncertainty analysis so that we can also understand uncertainties in the lab induced changes in snow albedo, snow melt, and runoff, etc. And then once we have these parameters, like the snow melt, runoff, we will feed those to a river routing model to assess the changes in stream flow and water resources in downstream regions. So there is a model called MISO-Route. It's a model developed at NCAR. And we will be driving this model. This exists outside WRF-Chem. So we will be offline driving the MISO-Route river model to understand changes in the stream flow. And then all the products that will be resulting from this project, they will be transferred to the NASA GMELT toolbox, where GMELT stands for Glacial Melt Toolbox. All right, so in today's presentation, I'm gonna mostly focus on the implementation of the brown carbon evolution scheme, the WRF-Chem tag tracer technique, and some advantages of chemical data assimilation system. This is an ongoing project, so we are nearly halfway through the project. Most of the developments have been completed, and we are currently running the model from 2003 to 2019. So the first thing I want to focus on is the implementation of brown carbon aerosols in WRF-Chem. Most of you may know that brown carbon is a light absorbing organic carbon that has a relatively strong absorption at UV wavelengths and weak absorption at visible wavelengths. It has much weaker absorption at visible wavelengths than black carbon. But there are a lot of uncertainties in brown carbon optical properties due to its complicated chemical composition. So brown carbon is directly emitted into the atmosphere. So it's a component of primary organic aerosols, plus it is also secondarily formed in the atmosphere. It absorbs solar radiation in the atmosphere, as its name suggests, and it reduces snow albedo after deposition on the snowpack, and so does it accelerate. It has the potential to accelerate snow and glacier melting. So most previous modeling studies have focused on the climate effects of black carbon and dust, particularly over snow-covered areas. So that's why that was another motivation for developing this capability to simulate brown carbon. And there have been several studies that advanced our understanding of brown carbon atmospheric evolution. And we try to represent that state of the art into our model. So this is the general workflow for our brown carbon implementation. As I said earlier, it has both primary emissions and secondary production in the atmosphere. So we need to account for both of these sources. So for the primary emissions, we have developed a parameterization um, to calculate the brown carbon emissions from the total organic carbon emissions that are available in current inventories. So that's what we call as primary brown carbon emissions. And I'll show you what that parameterization is. And then the secondary formation from the aromatic volatile organic compounds is also considered. So both the primary and secondary contributions, secondary components contribute to the bulk organic carbon, which is then subjected to the transport processes, including resolved advection, as well as subgrid scale processes like PBL mixing, diffusion, and convective transport. So this is just the emissions and transport part. We also need brown carbon to interact with the radiation. So the radiative properties of brown carbon, especially for both in the real and imaginary parts of refractive indices, we have taken those from the literature. So we took all the values and then did a best fit. And there are different refractive indices for the primary and secondary brown carbon, which means that we have to treat their absorption differently. And these then go into the Mie calculation and interaction with the radiation routine. But when the brown carbon is present in the atmosphere and it mixes with other chemical components, its absorption decreases with time. So that process is called photobleaching. So we also represent the photobleaching process into our model. And then finally, we implement their interactions with clouds in the same way. So we assume the same hygroscopicity for brown carbon as we do for organic carbon. And then brown carbon is subjected to wet deposition. We also do the dry deposition, both on the ground as well as in the snow. So the snow albedo reduction due to brown carbon, black carbon, as well as dust aerosols is then estimated through the CL and sneaker model within WRF-Chem. So this is a fully coupled atmosphere land surface snow model where we are tracking the deposition of all these light absorbing aerosols from emissions to deposition within the snow. All right, so these are the imaginary refractive indices of brown carbon. So the left panel is for primary brown carbon, the right panel is for secondary brown carbon, and all these symbols that you see, these are the refractive indices reported in different studies. So what we did is we took all these values and then we came up with a best fitted line, and we used the values from this best fitted line to represent the imaginary part of refractive indices into our model. This is our derived parameterization for calculating the brown carbon emissions, the primary emissions, and we calculate it as a function of black carbon to organic aerosol at the time of emissions. And we do this because both the black carbon and organic carbon emissions are available in inventories. So any standard inventory like Edgar, HTAP, CAMS, or any other emission inventory that exists out there include both black carbon and organic carbon emissions. And we did literature survey, and after that, from the literature we developed some lookup tables that fall along these solid circles, and then we did a fit to these this line for an easy calculation of brown carbon emissions that we provide as input to the model. The secondary formation in the brown carbon, we are using the Mozart-Mosaic chemical mechanism. So basically, the volatile organic compounds, they undergo through chemistry, which is mainly the reaction with OH radical, which then produces semi-volatile organic compounds that can condense, that go through aerosol thermodynamics and partition into aerosols. So because these are semi-volatile, there is a dynamic partition between the gas phase and aerosol phase. But there are many species that contribute to SOA formation. We assume that the SOA that is coming due to the processing of only aromatic VOC emissions, only those SOA contribute to the secondary brown carbon. rest of the SOA we assume it to be totally scattering, and that becomes a part of the normal organic carbon molecules in the model. The photo bleaching effect, which refers to the change of brown carbon absorption with the aging in the atmosphere, is also parameterized as a function of OH concentrations using this formula. And we use the same photo bleaching for both primary and secondary brown carbon. We set a minimum value that allows to remain at least 25% of the absorption of brown carbon. So if the model predicts that due to photo bleaching, the absorption due to brown carbon goes below 25%, we restrict it to 25%. Otherwise, it's a purely scattering aerosol, and there is no need to have brown carbon. So this is an assumption that has also been used previously, but it needs to be evaluated whether this is a correct number or not. All right, so this is all the processes within the model. We represent brown carbon come within our domain from the lateral domain boundaries. And again, we look at the literature to see what fraction of OC is brown carbon. And based on those studies, what we do is we assume that total 20% organic carbon from boundary inflow is brown carbon. So we split it equally into primary and secondary components. And then the remaining 80% goes to the scattering organic carbon within the model. Okay, so after this, these are this is our model domain. You can see that it's a big domain, covers almost entire Asia. And here we show the brown carbon primary emissions from biofuel burning. So out of all the sectors that we have in the anthropogenic emissions, only we assume that the biofuel burning is contributing to brown carbon and none of the other sectors, which is something that can be debated. But so far, we have not seen enough evidence of brown carbon emissions from fossil fuel burning. So we only consider it from the biofuel burning. And this is from the open biomass burning, which is derived from the FIN emission inventory. And this estimate is from the CHEMS inventory. And then we did a simulation for January 2013, and this is how the surface, the distribution of brown carbon surface concentration looks like. You can see that it is mostly following the emission distribution. The surface concentrations of brown carbon is higher in the areas where emissions are higher. What we are also doing, we are also calculating the brown carbon absorption optical depth within the model to see how the brown carbon absorption is changing spectrally. And as expected, as you can see, and you can anticipate from the spectral variation of the imaginary part of refractive index, we have strong absorption from brown carbon at 300 nanometer, which then decreases very sharply as we go into the visible bands. And you see there is very little absorption due to brown carbon at 600 nanometer. So because the absorption is strong in the UV part of the solar spectrum, and the UV part, which is here, it only accounts for about 8% of the total solar energy spectrum. So it implies that brown carbon absorption integrated across the whole solar spectrum may be small, and certainly it is much smaller compared to the black carbon. We have also calculated the direct radiative effects of black carbon. So what we show in the top row is the top of the atmosphere radiative forcing in this panel, surface radiative forcing in this panel, and atmosphere, which is just a difference between the top of the atmosphere and surface. And the bottom panel is for the long wave. So you can immediately notice that brown carbon causes surface cooling for short wave radiation by blocking the sunlight reaching the surface. And this is what we expect, means whether it is an absorbing aerosol or a scattering aerosol, they always cool the surface because they block the sunlight from reaching the surface. Second thing that we notice is that the brown carbon has a warming effect in the atmosphere because it is absorbing solar radiation, and that effect is stronger over the Indo-Gangetic plain compared to anywhere else in the domain. This may also be partially related to the fact that that we are using the simulations from January. So there is very little solar radiation in North China plain. If you remember the previous slide, the brown carbon in North China plain is even higher than the Indo-Gangetic plain. But particularly during this month, the absorption is more stronger over the Indo-Gangetic plain. The long wave effect is actually opposite to that of the short wave effect, but its magnitude is it is one order of magnitude smaller than the short wave effect. So the net effect of brown carbon aerosol is dominated by its interaction with the short wave radiation. Again, this is a very preliminary analysis. We implemented all these things. We wanted to make sure that the model works properly. It's not giving us weird values. We are getting what we expect to see from the model, and the detailed evaluation of brown carbon aerosols is under progress. We also look at the brown carbon deposition and snow albedo effect. And so this is the brown carbon total deposition. Again, this is very similar to the emission patterns. The total deposition flux pattern follows the emission pattern. The highest brown carbon induced snow albedo reduction occurs along the southern slope of Himalayas, like here, which is again because this is so close to the Indo-Gangetic plain, as well as northeastern China for the same reason, which also leads to the highest surface radiative forcing. This is an example from January, and we expect that the brown carbon induced snow albedo reduction that we see here, it may be higher during spring. So we still have to wait for the spring simulations to finish. But if you look at the numbers here of the brown carbon induced snow albedo forcing, they are really small. Like the highest value goes up to 0.05 watts per meter square. So we are waiting for our spring simulations to finish, which is when the transport of aerosols to the high mountain Asia is also more efficient, and there is more solar radiation available. So this is all related to the brown carbon. And the next thing, okay. Next development that we did for this project is to implement tagged black carbon tracers in the model to quantify the contribution of different countries to black carbon deposition in the Himalayas. So this is what we do. We are using a tagged tracer technique to do this, so that we are tracking emissions from these countries to in the same model simulation, so that we don't have to do multiple simulations. Now, one thing I would like to tell you that these tracers are artificial species added to the model that experiences all the processes that standard species do: emissions, transport, deposition, and chemistry. But they do not interfere with the physics, chemistry, or dynamics of the model. So basically, you can relate it to like a color scheme where you are tracking brown carbon or black carbon emitted from India as a different color, black carbon emitted from China as a different color, but at the end of the day, they all contribute to the total black carbon simulated by the model. So we have defined a local HMA region. So what we did is all the model grid points for which the elevation was greater than 1,000 meters, we classified that as local emissions for high mountain Asia. And you can see that a part of India, part of Nepal, part of China already goes into that definition of local emissions for high mountain Asia. So when I call it as an India tracer, it is not exactly the whole India. By definition, it is the part outside the high mountain Asia. And in addition to these regions, we also keep track of total fires, the contribution of total fires within the domain, anthropogenic emissions, which come from residential sources, vehicles, energy generation industries, and also we track the inflow from the domain boundaries to understand how rest of the world is contributing to black carbon deposition in high mountain Asia. So this is from a previous study, just to give you a demonstration that these tracers work. We implemented black carbon tracers in Mozart Mosaic in a previous study in 2015, where we wanted to use these tracers to understand the what controls the distribution of black carbon that was observed during the ICARB campaign in 2006. So in that study, we also defined some regions like North India, West India, East India, South India, Burma, and these dotted lines shows the ship track, ICARB ship track in Bay of Bengal and Arabian Sea. Uh, we do not know the initial conditions for these tracers. So we have to start with a zero initial condition, and we need to make sure that our model is spun up before we can use the model output for the analysis. So how do we estimate the spin up time for these tracers? What we do is we add up all the tracers, we call that BC trace, and we subtract it from the total BC. So at the start of the simulation, this difference is 100% because we do not know the initial conditions. But then as the model simulation progresses, which is what we show here, dates since the start of the model run, this difference starts decreasing and it approaches zero. So in this particular case, we saw that the difference between BC and the sum of tracers approached zero around 15 days. So we can maybe discard the first 20 days of our model run as spin up because this then stays constant for the rest of the simulation. This is an example of the ability of the model to simulate black carbon distribution along the ICARB ship track. And so the left panel here, left of this dashed line, we have the comparison for Bay of Bengal. And then on the right, we have for the Arabian Sea. So black is the observation and red is the model. So there are some uncertainties in the model performance, like here the model was not able to capture the observed level, here it was not able to capture the observed level. In Arabian Sea, the model is too low compared to the observations, but it captures the latitude gradients fairly well. Means like here it was able to capture high concentrations and then the gradients as we moved through Bay of Bengal to Arabian Sea. Now we use the tracers to see what emission sources were affecting the ship track during the whole campaign. And here the black is the anthropogenic sources, red is the biomass burning, and blue is the rest of the world, which is actually the black carbon that is coming from outside of our domain. So very interestingly, in the Bay of Bengal, anthropogenic emissions are the main sources, except for during this period when we had a biomass burning plume, which came from Southeast Asia towards the ship track. But this is how the tracers are very useful. So this peak here, the peak that we see here, this is related to the biomass burning and not to the anthropogenic emissions. But the peak here at the start of the campaign was more related to the anthropogenic emissions. When we move to the Arabian Sea, the biomass burning influence is minimal, and the black carbon distribution is mainly controlled by anthropogenic emissions from within our domain, as well as black carbon emissions that are happening outside our domain, or you can call it rest of the world. So this is how these tracers are useful. And then we look at the contribution of different Indian regions to black carbon along the ICARB ship track. So the top panel here is the Arabian Sea. And you can see that nearly 72% of the black carbon along the ship track in the Arabian Sea, those emissions came from South India. So South India was really the source for black carbon that was observed by the ICARB ship. When we go to Bay of Bengal, nearly all regions of India contribute significantly to anthropogenic BC that was observed in Bay of Bengal, with the highest contribution from Eastern India, and followed by Northern India. This is somewhat surprising because the Southern India is, Southern India is the second highest, Northern India is the third highest. And this transport from the Northern India is along the Indo-Gangetic plain and it goes through Eastern India. So this is a demonstration of how these tracers are useful to understand what sources are affecting BC in a particular region and where they are located. So we also used our 1 month simulation. We simulated the entire 2013, and we look at annual mean black carbon deposition in high mountain Asia. So you see that it is strongest along the edges of the high mountain Asia, which makes sense. The closer are you to the source, the higher will be the deposition. But then the tracers allow us to understand where these emissions are originating from. So now we look at the contribution of China, and China is contributing mostly along the northern and southern boundaries of the high mountain Asia, while the contribution from India are higher along the southern boundary. And in fact, the emissions from India are even penetrating to the center of the high mountain Asia. And this may be because of the higher convective transport, stronger convection that facilitate the lifting of emissions to higher altitude and their transport to the high mountain Asia from India. We also look at the contributions of different sources in different altitude ranges of high mountain Asia. So these 4 bars here, these are showing the contributions to surface concentrations, and these are showing the contributions to the deposition within snow. Interestingly, for the high mountain Asia altitude ranges between 1,000 to 2,000 meters, China dominates the contribution. Nearly 50% of the black carbon surface concentrations are because of emissions in China. But as we go to the higher altitudes, the contribution from India increases and that from China decreases. Another interesting aspect of this figure is that look at the yellow color, which represents the total biomass burning from Asia. And it can contribute up to 25%, especially at lower elevations, but this is also a significant contribution to black carbon deposition and concentrations in high mountain Asia. The rest of the world, which is these brown colors, the rest of the world can also contribute around 5% to black carbon deposition and concentration in high mountain Asia. And the local emissions, which are shown in the green color, their contribution is very small to black carbon deposition in Asia. So this is just 1 year analysis. We are doing more simulations. So we are simulating 17 years. We will be repeating this analysis for all the 17 years to understand how much interannual variability there is and if these results are consistent across years. Okay, so this brings me to the final topic, the need for chemical data assimilation. We know that our models are uncertain. There are so many uncertainties. Our emissions have uncertainties. There are some processes that we do not understand very well. So how do we address those uncertainties? And we learned this during the development of our Delhi air quality forecasting system, that assimilation of MODIS AOD can significantly improve aerosol simulations over India. So this is the here, this is a comparison of the frequency distribution of AOD observed by MODIS in black. The WRF-Chem AOD predicted without assimilation in red, and the WRF-Chem AOD after assimilation of MODIS AOD in blue. So you can see that blue and black curve almost overlap each other. If you look at the average values, the MODIS value and the WRF-Chem with assimilation values are almost similar, with a little bit shorter standard deviation. But this significantly improves the aerosol burden in the atmosphere. And for this period, because we were focusing on the crop residue burning season of 2017, most of the changes in surface PM2.5 due to assimilation was also occurring in the crop residue burning region, like Punjab and parts of Pakistan, Haryana, and Delhi. This whole belt benefited the most from the assimilation of MODIS AOD. So, but this is just assimilation. Unless we compare it to the surface observation, we do not know whether or not this assimilation is helping and pushing us in the right direction. So here, this is a busy figure, but I will try to go quickly through it. Here in black, we have CPCB observed PM2.5 at 24 stations in Delhi. In blue, we have the WRF-Chem experiment with the assimilation, and we also allow aerosols to feed back to the radiation. The red curve is WRF-Chem experiment without assimilation, but we still allow aerosols to feed back to the radiation. The green curve in this figure is the WRF-Chem experiment with MODIS AOD assimilation, but we do not let aerosols feed back to the radiation. So you see, for the most part, the green and blue curves, they overlap with each other. But there is a difference between the blue and green curves when we have the most acute air pollution episodes in Delhi. And the difference between the blue and red line give us the benefit of improving the initial conditions because of assimilation, plus also the importance of aerosol radiation feedback. Whereas the difference between blue and green line tells us the improvement only because of aerosol radiation feedbacks. So on average, we were able to improve, reduce mean bias in the first day forecast by 86%. The second day was about 81%, and the third day was about 70%. And about 75% of these improvements in the forecast resulted from the assimilation of MODIS AOD, and about 25% improvement is due to interaction of aerosols with radiation. If these aerosol radiation interactions becomes particularly important during acute air pollution episodes because the difference between the blue and green line increases. Now, these benefits, they are not just limited to air quality forecast, but they also translate to the weather prediction. So here, this is the same scheme. And now here we have an improvement or reduction in mean bias of temperature by 17 to 30% during different days. And interestingly, we get the maximum improvement in the temperature forecast on the second day. And one reason that we think this is happening is because we have to refresh our initial conditions every day when we run the model. So the aerosol radiation interactions that have accumulated over the 24 hours, they need to be wiped out in order to start a new forecast cycle. But then as the forecast progresses, these feedbacks also accumulate. And that's why we see the maximum improvement on the second day. And the improvement on the third day is also even higher than the first day. So for a project like ours for high mountain Asia, this is important because we are not doing any reinitialization. So these feedbacks will keep accumulating, and hopefully our predictions will be better. This is just a demonstration of changes in the shortwave downward surface reaching shortwave radiation. So over this region where we have the highest pollution, due to the assimilation, we get a decrease, or an average decrease of about 100 watts per meter square. So this is very important for the solar power generation, as we know that we are now moving towards renewable energy resources. So having wrong aerosols in the models can lead to wrong predictions of the solar radiation, which can be which can lead to large losses for the companies that are investing in solar-based energy production. The PBL height also reduces because of this increase in aerosols, and it decreases by about 500 meters on average, which means that now we will be mixing the emissions into a smaller volume. So this AOD assimilation also induces a positive feedback that increases surface PM 2.5 concentrations by limiting the mixing of emissions into a smaller volume. So all our developments are complete, and we are now actually running the model. This is a data assimilation. This is the model workflow that we are following every day. We are assimilating MODIS AOD and MOPIT CO 4 times every day. So what we do is we start the model at 0Z every day. We run it until 3Z. We stop it. We assimilate the data. Then we do another 3-hour run, we assimilate at 6, we do another 3-hour run, assimilate at 9, another 3-hour, assimilate at 12. Then there is no retrieval for the rest of the day because the satellites have moved to the west. So we do our last run from 12Z to 0Z next day, and this cycle continues every day. So we are currently, as I said, we are evaluating the simulated aerosols in brown carbon by comparing with observations, including surface organic carbon measurements, MODIS AOD, OMI, absorption optical depth, aeronet absorption optical depth, single scattering albedo, OC in surface snow, surface albedo, snow cover, surface temperature and precipitation. The production run is ongoing, and we have completed almost 6 years of run so far, and analysis scripts are under development. So with this, I'd like to thank you and take any questions.
Thank you, Dr. Rajesh, for such an interesting and informative talk. And I'm sure it has been quite an enriching experience for all the viewers. I would like to quickly take up a question on the YouTube chat. The Prajwal Singh Rawat, he is asking, the Indian satellite INSAT 3D also provide high resolution snow cover. Are you using or planning to utilize INSAT 3D product?
Thanks, Prajwal. I was not aware of this product, so thanks for mentioning it. We would like to use it.
Okay, so we don't have any more questions as of now. So attendees, if you have any question, you can definitely post it on the YouTube chat box. Okay. I think that's it, Dr. Rajesh. Thank you for accepting our request and delivering the talk in such a short notice. We would hope that we will have the opportunity to hear more from you in the future. And on this note, I would like to thank the Director IITM and Computer Division for the support towards conducting this virtual seminar. With this, we would like to conclude this session. Thank you, everyone.
Thank you, Shwezi.